Hello and welcome back. This will be the second video, section 1 2 that's coming this week. It's on domain and range. Now we talked about functions quite a bit, but now we're going deeper into particularly the domain functions. Again, functions is the single most important unifying element in all of calculus, and so domain being a specific part of that is quite important. Each of these, both of these are a set of numbers. A domain, each are a set of numbers. So we just want to describe. We just want to describe that set of numbers. So there's several ways to describe. We want to describe these and say, suppose it's an inequality. X is greater than A. All the x's that are bigger than A. It would look on a graph. It would look like A is here, and we're trying to all the x's that are bigger than A, and then there's something called interval notation, and that would be all the x's that are greater than A would be A infinity, and it's open. If this had let's use a B. If it's inclusive, all the x's less than B, well, here we go, B is here, and we want to describe all those x's. By the way, this is a closed point or a bracket, whereas this is an open point because it's not included. So this, in interval notation, this would be everything going down to negative infinity to B, and B is included. We'll do one in between. A less than, what do you see in D? C is less than X, less than or equal to D, for example. C is less than X, less than or equal to D. And so here on a number line, C would be here, D is there somewhere. This is a closed point, this is an open point, or, or like that. And then you just kind of color it in. And so that's a way to do it. In interval notation, C is open, like that. Interval notation, that's what we're shooting for. That's mathematicians, that's the way we would denote all these sets of numbers. Domains and ranges. Where's the eraser? Okay, I'm going to erase this stuff, and on we go. Ways to denote. There's also another one called set builder, which I guess we'll get to. Find domains. So you find the domains of functions. Find domains of functions. All we want to do is find a set of find restrictions. Determine restrictions, and then those would not be in the domain. And I'll get to that in just a second. But first, let's use a polynomial function. A polynomial will be something like this: x cubed minus x squared plus 3x plus 2 something. It doesn't matter. A polynomial function. The point is the domain of polynomial. All the reals. That's interval notation, but when it's all the reals, that means all the reals. All real numbers. For any polynomial function, by the way, the range of a polynomial function is also is also all the reals. Any polynomial function on a graph will span from negative infinity to infinity, up and down, and right and left. Domain, range, all the reals, for all the polynomials. So then you say, well, what are we doing then? Well, what's this restriction stuff? Well, let's do this. Something called a rational function, where it has, a rational function is a fraction. And x's are in the top and bottom. 2x plus 3, for example, over x minus 2. Okay, so everything's okay there. We can put any x at all in, except when the denominator is 0. You can't divide by 0. It's impossible. I can show you that real easily sometime if you really want to see it, but it's impossible to divide by 0. So what you want to do is you set this denominator equal to 0, except for x, so x minus 2 equals 0, so x is 2. So you say, well, what's the domain? Well, in interval notation, it would be negative infinity to 2, and then 2 to infinity. These are open. That means it's not including 2. The way I would do it is a domain. I'd say all the reals except e. Come on. X equals 2. All the reals except x equals 2. So anytime you have a rational function, fraction in the bottom, you set the denominator equal to 0, and you solve it. Then it's all the reals, except for the solutions to that, which could be quadratic. This could be quadratic. And then there's another restriction, another type of function that has a restriction. It's called the square root function. A radical function, rather. Sorry about that. And that has, that has a radical in it. F of x equals, let's see, square root of x minus 8. Something like that. Okay, so you can put anything in here. You can put 10, 12, 15, 100 in there, but the square root of 100 minus 8 is square root of 92. That exists, but you cannot ever, well, not ever, you cannot have a negative under the radical. It leads to an imaginary, that comes in calculus where we do let a negative under the radical, but you can't have that. So for a radical function, you just say x minus 8 has to be bigger than or equal to 0. And it has to be greater than 0. You have to have a positive number in here, or 0. And then you solve this. X greater than or equal to 8. That's the domain. All reals, x greater than or equal to 8. Or greater than or equal to 8. Put any big numbers in there, but you can't put anything less than, it's supposed to put a 6 in here. 6 minus 8 is negative 2, square root of negative 2. Can't do it. So that's that. Oh, good. Set building notation. I should just mention this. Suppose you have a domain, let's see, from negative infinity to 2, and then from 2, negative infinity to 7. There's something called set builder. This is the importance of this, and this sign is called, the bracket is read as the set whose members are x such that. The set whose members are x such that. Here, x is an element of negative infinity to 7. I'm going to stop. I'm going to stop with set builder notation. By the way, that stands for all reals. That's set builder. But what we want to do is we want to concentrate on interval notation. So that's that. Domain from a number line. Domain range from a graph. All right. Trying to stay out of the way this time. I was watching the video and I'm like, I'm in the way the whole time. Domain range from a graph. Okay. Here we go. Just a couple of them. Here's, something like that. Here's one with maybe go something, like that. I'm just drawing pictures of functions. And this is what we talked about in the last video. The domain is along the x-axis. And I think I used different colors last time. Sorry about that. The domain is along the x-axis. And so you can look at it this way. Those are the x's you can put into the function. The range is along the y-axis. That's the range. Oh, and I'm standing in front again. Here, the range is much smaller. It only goes from that to that. You know, that's a pretty small range. But the range is that. It's what you get out, the output of any function when you put a number in. So that's how you can identify it from a graph. Now, if I actually draw a graph and put in points, we'll just do it with one of these. I wonder if I have one drawn. I do. You know, I mean, I'm going to do points. 4, 3, 2, 1, 1, 1, 2, 3, 4, 5. How about we start here, and this function looks like so, and it goes up to there. That's included in it, and now we have to do the range. 1, 2, 3, 4, 1, 2. So this point, this is the point, -4, -2, and this is the point, 5, 4. Okay, those are the actual points. So what we want to do is the range is going from -4 to 5. It takes on all the values from -4 to 5. Range. -4, 5's included. Oh, excuse me, I said domain. Come on, Brad. Domain. Sorry about that. Range. Hope I wasn't saying the wrong thing. Range is going from -2 to 4. There we go. Set notation. That's set notation. I could do interval notation. This would be -4, 5. 5's included. -4 is not. I would go -2, 4. 4 is included. -2 is not. But this is the domain. Domain. Range of that function on the graph. So then, I don't know, at the very end of the last time, we were talking about toolkit functions. And Stop.